No.
All right, everybody, we're going to get started. Thanks for coming to today's CGD seminar. I'm thrilled to be introducing our speaker, John Dennis, today. I had the distinct pleasure of working with John and his team during my first 4 years here at NCAR, and I know firsthand like the great work that they do. One of the examples that I love, and I was telling some students about this one a while back, is this Samurai code that they got from CSU, and the professors were like, could we make it a little bit faster? And John and his team got 120 times speed up. So what took a month to run ran in a few hours. So he's really an expert, not just at NCAR, but across the world in optimization and new technologies. And he's been working extremely hard with the not easy to work with Exascale Tiger team. We had a lot of different perspectives. And he's gonna share this, some of the outcomes of this, basically finding a coherent, balanced message about what we can do with new technologies. This was far from an easy task, so please let's give a warm welcome to John and hear what he has to say.
Thank you. Can you hear me? Okay, cool. So the magic that Brian said, mentioned. This is not a standard kind of result, and it was the work of a lot of people contributing, making different contributions. But thank you for that introduction. So what we're doing is we have this is the Exascale Tiger team, names included here, and what we're doing is we're going around to all the laboratories and kind of providing a standard talk that's general for all of NCAR for the first part, and then the second part is specific to each laboratory. The Exascale Tiger team, the goal was to determine the best course of action with respect to the utilization of exascale technology. So we want to be kind of aware that we're talking about exascale technology versus an exascale system, because you're probably not going to get an exascale system here at NCAR. You will be using systems that are built with exascale technology. And so what do we mean by exascale technology? GPU enablement, lossy data compression, parallelization of post-processing workflows, and cloud computing. So this was an NCAR-wide committee with the various members listed there, and they all contributed over quite some time. I'm not going to reveal how long it took us. So what we did is we created a recommendation on two sources of information. One was a UCAR-wide survey, and another was laboratory-specific focus groups. So we went around and interviewed in group form various scientists, and in CGD there was software engineers as well. There was so you got 3 feedback sessions in CGD, and so that was actually the largest of any of the laboratories. So, and we asked the question, what science would you perform if you could magically eliminate limitations? And this was kind of fun because it got the side. I really enjoyed this because you got the scientists thinking and kind of what really excites them and what would they do if. And we didn't define limitations because we wanted them to say, I don't have enough compute power, I don't have enough disk space, I just don't have the people. The graduate programs are not graduating the right kind of people. So this was a free and open kind of discussion. There was we came up with one overall set of recommendations for the NCAR directorate, and then 7 laboratory-specific recommendations. And we consider this a starting point for future discussion. And we want the discussion to be ongoing. So just some of the background in computing trends. I've already briefly mentioned exascale system versus exascale technology. NCAR scientists today have access to systems that are based upon exascale technology. And whether that be in derecho, in the MWSC, or in other DOE facilities or other NSF facilities. One of the other things to kind of keep in mind here is that the cost of electricity to run an HPC center is significant. There's been some discussion, I don't know how many of you are familiar with this net zero initiative that UCAR is pushing. And so they want to kind of redo all our buildings and do a lot of energy efficient improvements to some of our shuttles and stuff like that. So they project that in 2030, 63% of NCAR's carbon emissions will be from the supercomputer. That includes airplanes that we fly around, buildings, cars that we drive. So that's significant. It'll be the main source of carbon from this institution. And one of the things we don't, there has been, GPU-based computing is approximately 3 times more energy efficient. I would have loved to calculate this myself using the ASD projects that recently happened, but this is something from Mark Taylor. So again, this is in the climate community. And so what this means is, then CPU, what this means is that big science means you need to be energy efficient. That needs to be a consideration. So overall findings of the ETT committee. NCAR staff aren't broadly practicing exascale software development. And they're citing, we hear this kind of over and over, there's no explicit prioritization from the leadership, either at the NCAR, UCAR level or at the lab level. There's not the funding to do this. Staff skills and familiarity with new technologies is problematic. And again, we hear this over and over, the time to shift to new paradigms while still getting what the expected workload done. And another one was meaningful cooperation between scientists and software engineering with respect to modern HPC and exascale practices. So some of the other findings we came up with, that all throughout the institution, novel science outcomes could be enabled through the use of modern HPC and exascale capabilities. This was consistent. And some laboratories had a large number of them, some laboratories had a smaller number of them, but everywhere novel science could be being done. We also believe that prioritization, funding, and staffing needs to be part of the LCPO and NCAR strategic plan. This is not just like, can you work on this in your free time after you finished all the other stuff that you've done. You have to be intentional about this. And we also thought that cross-laboratory software development activities are a potential opportunity to build on this. So ETT recommendations for NCAR. Modify NCAR and LCPO strategic plans to explicitly include response to exascale technology. So, this is basically commit to something, and we're not saying what you should commit to, but commit to something and then work on that. Foster a co-design culture where scientific objectives represented as a collaboration between scientific and software engineering leadership. I think, this is kind of varies throughout the institution, but I think this is really critical, or we believe this is really critical, excuse me. Identify internal and external funding to advance specific responses to the ETT. So this is not going to be done with, again, the existing budgets or the existing personnel, or without a personnel augmentation. So, and communicate to staff the importance of exascale technology has on the scientific mission of NCAR. So this is probably yeah. And so the complete list of recommendations you can get on the hyperlink that I guess doesn't work in an in-person meeting. So, so for CGDs, specific recommendations. some CGD science appears to be exascale friendly. Not all of it is. And this is one of the challenges, I think, is that CSM supports so much diversity of science that some of the science objectives are great fits for exascale and some are not. And we also found that CGD is not really well positioned to at the moment to leverage exascale technology. Pieces of CSM are GPU enabled. Lossy data compression is not integrated yet into the code base, and not all post-processing pipelines are parallel. The good news is that there are multiple existing investments in GPU enablement. The MPAS-A dynamical core, Puma's various microphysics and radiation packages mentioned there. And okay, so now I want to talk about exascale friendly science objectives. How were they identified? Okay, and these that are science objectives that can benefit from exascale technology. This may or may not be aligned with overall institution or laboratory science objectives. That's kind of not our goal, is to say that these particular science objectives are important. We're just saying that exascale technology can help these. And so it's your choice of whether that matches with your overall objectives. And we kind of broke these down into 3 categories of science objectives: modest, which it could be achieved today but with a better allocation next year. We thought these were kind of uninteresting. There was the unlikely, which is not going to happen probably in the next 20 plus years. But the interesting is currently not possible or easy, but possible in the next 3 to 10 years with significant effort. So this is where we're going to focus on this in the next slide. So that's interesting science, and that's not So here's some of the science objectives that we thought were interesting. So the high resolution seasonal to sub-seasonal prediction capability. This was actually this was described by Jager Richter a couple of months ago in a nice talk. So this could benefit from GPU enablement, lossy data compression, and parallel post-processing. Other large ensemble projects like the perturbed, I think this is right, perturbed parameter experiments, large ensembles. This could all benefit as well from exascale technologies. Convection permitting ensembles and biogeochemistry and eddy permitting oceans. These are kind of on the far end of interesting. And I said yes, or maybe, excuse me, on the biogeochemistry. That's kind of, it's somewhere between interesting and unlikely, and I don't know exactly where it fits. So anyway, so there's plenty of interesting science friendly, or excuse me, exascale technology friendly science objectives. There's certain objectives that are not particularly exascale friendly, like climate change or paleoclimate. This is just one of their features. All right, so specific challenges for CGD. One of the ones that really kind of stood out was unclear how a diverse set of scientific priorities are balanced. And this was a long statement, but I'll read it anyway. Long-term strategically important investments to respond to changes in computational infrastructures are being sidelined due to short-term deadlines. And so, and that's, we think, and this was kind of recognized by that 48% of the survey respondents indicated that there was moderately or severely impacted by people. So this is the people either to do the software development or to actually run the performance or to actually perform the science itself. There was limited computational resources by 56% of the respondents. So this was lower actually than a lot of other laboratories. So this is telling me that in general, people don't see a need or a lower, maybe I shouldn't go there. Anyway, but the thing that really stuck out, maybe I should point that out, disk storage. 89% of the respondents said that this was a problem, that it was moderately or severely limiting the science that they could perform. So that really stuck out, and that was one of the highest of all of NCAR. And data analysis of large data volumes is difficult. This was also a kind of a universal statement. All right, so again, how do you determine which science objectives to go after? We're recommending that scientists and software engineers make intentional and strategic decisions on software developments. I think that one of the feelings that we got, at least from looking from the outside, is that people are given 7 things to do, which is way too many, and they end up doing 3 things. And then the question is the 3 things that they did actually the most strategically valuable? And it's not clear to me that is happening. Or there's limited computational resources. We're suggesting to adopt an explicit approach to GPU support. Right now, it's kind of unclear. I think there's a couple of different options here. A level 1 would be to test and support GPU-enabled code provided by the community. As of a couple months ago, this is still not occurring, unfortunately. And a level 2 is identify internal and external resources for GPU enablement. So this is much more aggressive. You say you want to go after that, and that would require resources. But I think that a level 1 is really critical, because if somebody hands you a piece of GPU code, you should be able to use it and make sure it doesn't break by updates that come in at a later time. Limited by disk storage. So there's really 2 tasks here, and I think that you shouldn't convolve them together. Implement lossy data compression capability. So this is a task that makes perhaps done by software engineers. It's in the model. You can turn it on. You can choose to turn it on or not. The other one, which is evaluate the scientific impact of lossy data compression. This is, I think, done by scientists. And so these are 2 different tasks. And I think that we're concerned that if you wait for the scientific impact of lossy data compression, then other people that may have different standards or different that could use lossy data compression don't have that capability. And then data analysis, encourage CGD staff to join and participate in the STS community. I think you're one of the more active groups in that, but that's kind of a general recommendation for. So I think that's it, and I'm hoping that I get a lot of questions.
Thank you very much. I'll say for anybody online, there's the Slido. I think it's hashtag CGD seminar. So if you put questions there too, I'll ask them. But anybody have questions? Yes, Dan.
Thanks, and thanks for all the work on the Tiger team. I wondered if you could elaborate on your statement that the GPU capabilities maybe do not lend themselves to climate and paleo.
Sure. So climate, the characteristic of climate and paleo is that you want to collect a lot of statistics. So you're not running these for 3 days simulation. You're running it for 500 years, or with paleo, 10,000 years. And so you need a very small problem. You need a very small problem that runs quite fast so that you can collect enough statistics to make these evaluations. GPUs do better when you give them a very large problem. So if you're doing weather forecasting, which which in general you're not, So if you're doing weather forecasting, then you can throw a very large problem at it, and you can do as much as you can do, in the real-time weather prediction constraints. So some of the large ensemble kind of work, you're looking for shorter time scales, and you have multiple ensembles, so you can parallelize over the ensembles, and you don't have to run at the maximum rate.
Yeah, thanks. Follow up, I guess, to reframe that, can you think of ways, maybe unconventional ways, in which GPUs could be leveraged for climate and paleo? I guess, in the traditional framing, as you're saying, right, we're interested in these very long integrations that maybe do not lend themselves to parallelization.
Mm-hmm.
Should we start thinking about, for instance, initializing large ensembles from multiple time points, maybe starting from a lower resolution? Should we be thinking more about emulators and other technology that's meant to be run on these GPUs? Do you think that these are, should we be thinking in that space if we're going to be kind of deprioritized by this technology in the future?
I think you should be, and it's really a scientific discussion of how critical, what's your ensemble size, right? And whether it's scientifically valid to kind of initialize from different, time slices. But the traditional, start in 1850 and run for 500 years, that's not a good match.
Okay, thank you for giving this presentation. It's very interesting. It sounds like a lot of work. I have a question regarding community support for like GPU-enabled codes.
Yeah.
Because this summer I went to the WRF MPAS workshop,
Mm-hmm.
and they don't yet, as far as I understand, have a GPU community support for MPAS Atmosphere, which is a much simpler system than CSM.
Correct.
And Michael Duda was really worried about like supporting GPUs, but I suppose there's a lot of dependencies on who is the vendor and what compilers are used, et cetera, et cetera.
Yeah.
Do you have any thoughts on that, on how do we proceed with that? Because he was very worried about it.
Well, I think you need to, I think you need open standards that can, okay, so you need to have code that runs on both CPU and GPU. I mean, that's a given in my mind. And one of the approaches, then you can say, is it a directive or a language-based approach? And so, yes, it is a support issue. I don't think it's something that you can do just by giving it to one person and saying, okay, this is what you're going to do on a Friday. This is a big deal, and this is a. I think that you can. I think that you can write fragile code or you can write robust code, and it's. I mean, I'm sure that the first MPI code that came out was quite fragile. And nobody, if you blew on it wrong, it would break. But that's kind of a standard. You don't put out a version of CSM today without MPI. I mean, it's just the way the code is. So.
Thanks, John, for a good talk. First, I want to take issue with your statement that GPUs are 3 times as energy efficient as CPUs. That's a very subjective number, and technology is changing so fast that you can't. I don't think you can make a statement like that.
It was so the ASD run that we ran was pretty consistently 3 to 4 times more energy efficient. This was this summer.
Okay, so maybe qualifying it would be something you could do there.
Yeah, and of course you have to have efficient code. This is not comparing inefficient GPU code to efficient CPU code. This is efficient CPU code to efficient GPU code.
And then one more thing, and then I'll give Dave the mic. Uh, oh, inline data compression
Yeah,
is totally feasible, totally possible right now.
yeah.
But it's based on HDF5, which has very poor parallel performance. I'm wondering if you've looked at the possibility of improving HDF5 parallel performance, or some other technology to compress data.
Uh, so what we didn't, one of the, okay, so one of the things we didn't want to go down because, well, we spent quite some time with it. It was like, do we use this particular technology to achieve this end goal? And then we would, like, do you use HDF5 or do you use CUDA programming, right? And then we'd get into arguments that would last for months and months on end. And so, we're not making specific, kind of like programming model recommendations on this. I recognize that there's, the data compression is a little bit tricky on how to do this. You could say maybe you do it offline or something. I don't know, or inline. Maybe Allison, do you have comments on that? Maybe.
You have to use the mic.
I guess my main comment is that I wouldn't just not do it because we don't have the technology worked out right now. I think there's plenty of room for the scientists looking at data and deciding what's acceptable levels. And I feel like the technology has come along a lot since we started talking about this 6, 7, 8 years ago. And so I feel like, if there's support for doing it, we'll be able to work out a solution and that we shouldn't throw our hands up.
Yeah, I mean, one of the key messages that came out of it was that almost everybody in CGD could benefit from, data volume reductions, right? And so that could like impact the whole community, where some of these other technologies would impact people at different rates.
Another thing is you can reduce data other ways besides using compression. You can put a lot of thought into what data you're outputting, and if you're outputting stuff that isn't being used. This is a conversation I've had with Gary Strand a lot about some of these projects output 500 variables and everyone looks at the same 10. Not outputting stuff that you don't need is the easiest way to reduce your volume.
And maybe I'll just clarify. I think where Jim was going with this is I think we're all in agreement with offline data compression, but inline, if we can compress and write less output, but it takes 40 times longer to write because the formats aren't efficient, what's the solution there? Is there, do you guys have recommend? I know Sizzle looked at like ZAR and NC. I think you've looked at NC-ZAR. Like, are there methods that beat HDF5 that are viable for our community?
Yeah, that would be Hying's the one that has investigated all that, so I can't. Yeah.
A whole bunch of questions, and I just want to follow up on this one. I want to have this conversation more on the compression CSM, process. I think we need to, figure it out. So I want to understand all the limitations and possibilities. And I kind of agreed with your statement that we shouldn't let this, our lack of understanding of when we can and cannot use it for scientific purposes stop us from building the technology to be able to do it one way or another. I think we've been in this loop of we're saying waiting for one or the other to dominate, and then it affects we do nothing.
Yeah.
But maybe I don't fully understand the situation. I have one small question, which is just you said in terms of the GPU support, a directive versus language based. I don't really understand what you meant by that. Do you remember what you even said or what the context was?
So a directive-based approach could be you can take the existing code base, whether it's it's mostly written in Fortran, and you add directives, or you add ISO language standards to the code base, and then you can then it's a compiler will kind of change, you know, whether it's GPU targeted or CPU targeted. A language-based approach is more kind of a more aggressive kind of intervention. Maybe you consider ISO-Fortran a language-based approach. You know, if you look at what DOE has done, they've done these C++ productivity languages, and that's kind of a very high resource-intensive solution, right? And so the directive-based approach exists in the code today, and that's basically what all these GPU-enabled pieces use.
Okay, thanks. I think
Yeah.
that's what I thought, but I want to hear you. So my real question was that first bullet there. You know, you didn't really mention about, you know, how that might be limiting us. Like if we don't have an exascale machine readily access to, then is that depressing the drive to push towards exascale technology? And
Well,
also, you just, yeah, go ahead.
well, I was going to say a lot of people got stuck and said that NCAR, we're never going to see an exascale computer. And so why should we worry about this? Well, the reason is that derecho looks like a little piece of an exascale computer that the DOE, you know, that the DOE is deploying. It looks like Perlmutter. Perlmutter is a pre-exascale system, right? And so the next generation, you know, the systems that we have access to in-house will be using that technology, right? So we need to be able to use that technology, even if we never achieve a large enough system that's an exascale. I would love to be wrong on this bullet item, just incidentally.
And so is the main potential access is DOE for the time,
Yes.
for the time being,
Yeah,
if we,
I think.
I think that was almost my question as well, but maybe I'll phrase it in a different way. So, you know, climate science has kind of relied on increasing its capabilities through good science, of course, but then it's through increasing complexity or increasing the ensembles or increasing the thing. And that's been driven by computers getting bigger that we can invest in. And so I think the ratio is 3 times the size of the previous one, which is a good thing there. What I'm trying to ask really is you know, if we bumble along and don't worry about this too much, where does that leave you? What would be the implication of the next computer after that one? Do you think that you could still buy a CPU machine of the size that you've got now, or even 3 times bigger, or will you be actually not even? Will you be shrinking because of the way that the manufacturing's going and with the chips? What, you know, is there a cliff here that we should be worried about, or is this just like a nice to have?
I think there is a cliff that you should be worried about. I'm going to refer you to Thomas. About you know, about what that looks like going forward. It's but you know, if you look at the you know, it's expensive to run the electricities of these systems. So you're gonna be at risk for having your science limited by the size of the CPU system. Okay, so if you kind of don't engage here, you're going to risk your science being limited by the size of the CPU system that you can get access to, right? And so you're not going to. I mean, we already see it today, is that we're not getting DOE allocations. Decades ago, you know, we regularly got DOE allocations. Not so much anymore.
Can I ask one last question? Do you have a perspective on the thing that you explained to Dave? But I wondered whether you've got a perspective on it, on the relative balance of something like the difference between using separation of concerns. So Fortran is still being used, and there's code generators or something like that, versus writing in C++, to be frank, or something like that. What the right path is here for this?
We ended up arguing for months on that, in the meeting. You know, I mean, I think my group has been kind of pushing on the ISO language standards and directives based because there's such a huge investment in existing Fortran code that it's not reasonable to think that you can rewrite it anytime soon. So, and you know, and the truth is that the directive-based approach does quite well.
So I had a comment about the what variables one saves, and then also a question for you. I just want to, I guess, point out that for a community model, I'm not sure we have a great mechanism of knowing what variables people would want that aren't currently saved. You know, so like I've certainly had the experience of trying to analyze archived runs where we don't have the variables that we want for our science, you know, for comparing with observations, for example. But like I don't think there's a way to know that, right? No one else, Dave knows that, but no one else, right? So so it's just when we talk about like not saving variables, I guess we just should be careful about that, because we could risk, you know, not being able to do science and not even knowing that science wasn't able to be done, because, you know, at the goal of trying to compress our data. But then my question for you was basically, you mentioned all the interesting ones. What were some of the modest things? Like, what were some of the things that are like this year or next year could be done in this space?
Oh my goodness. I don't know. I'm blanking. The truth is, I talked to about probably about close to 100 scientists around in car, and so I'm having trouble accessing that for CGD specifics. I mean, I think, you know, I think that. So I'm sorry, but I. Yes, the report is available, and the notes is not generally accessible. So what person said what, so.
I want to expand a little bit on what John sort of was talking about in terms of like the cliff and what we need to do to avoid the cliff. So what we do a lot here in CGD is, of course, climate runs. And we do large ensembles of climate runs. And so if you foresee us there being a cliff unless we adapt, what should we be doing? Because there still is going to be a need to do these types of long climate simulations. And so I mean, is it what you're talking about, like the directive approach with the ISO? I mean, I'm not really sure. I'm not a software engineer, so I really don't know.
I think you need to be, I think a directive or ISO Fortran based, or ISO, I say ISO Fortran because that's, you know,
Okay.
Probably a directive or ISO based Fortran approach. You need to be able to absorb that from the community, test it, and make sure that it doesn't break. I think that's a critical one. You know, but it's also, I think the cliff is actually probably closer than you realize.
So we need to build a slope to avoid the cliff. But, you know, I'm just sort of thinking in the future, right? I mean, you know, so that these techniques that we will build in to try to create that slope is going to help us limp along. But what's the ultimate solution here?
You know, I think the critical thing here is you want code that can be targeted at you know, either a GPU or a CPU based system. And, you know, I'm not even going to go into some more exotic architectures. So that means that if you had such a code, then if you saw a big DOE system, you could switch, you know, turn a switch and run on the big DOE system. If you had a CPU system, you could run on that. And you know, and then if you had the choice of both of them, you could say, okay, this one's more efficient for my science objective, and go with that one.
And my final question is, in another 20 years, is this, so what's the next thing? Is there going to be like a radical change after? I mean, what is there a buzz, out there
I'm
that says
retired.
like, oh, after there's this,
Yeah.
thing in the future that we're going to have to trash GPUs and do something else.
I'm going to be retired in 20 years. um, so it's hard to prognosticate. I would say that it's hard to prognosticate 20 years out. And so, but I mean, this is. I mean, there's always going to be change, right? I mean, I am confident that sometime in the long ago past, people would write serial code, and then they would go to their software engineers and say, "Can you get that message passing stuff to work for me?" Right, and then they would do that, and then the scientists would come back and say, "But that's really not the newest science that I have. Can you port this next version to the MPI so that I can run it?" I mean, that obviously stopped, right? I mean, it's we support, or not personally me, but MPI code is supported in there. It's a standard, and everybody knows how to turn it on, and maybe a more limited subset of people know how to go into the internal guts of it and do that. So I think, and that was, so, there's always going to be change. And do you build your structures and your so that you can adapt to the change?
I just want to build on that question that was building on the question I asked, which is, can we get away with weak links in the chain? Is there a prioritization we can do here in terms of being ready for sort of the GPU or the hybrid chips, whereby we might have some bits of code that are not great for that, but they're not the most expensive part of the code, and you can get away with it? Or does that weak link break everything? To what extent do we have to, CSM is quite big, right? It's got a few lines of code, and
Yes.
if you go through everything and you say everything needs to be looked at and made better,
Yeah.
that's a lot of work. If you went, let's look at all the really big chunky bits that are doing a lot of the work, is that a solution, or does that not work?
It's hard to answer that question. So one of the features of GPU code is that the performance looks absolutely miserable until you get it all on the GPU. And so, you'll be going through and you'll be saying, oh my gosh, I've got a factor of 17 slowdown. And then one day you get the final bit on there, and then you're like, it's 4 times faster, right? And so you kind of have to get a lot of it. But I guess the broader question is, do you leave stuff behind? Do you leave stuff behind that was written 20 years ago that 2-3 people in the community still use? Maybe you have to make the intentional decision to leave that behind and to take the consequences when they're frustrated and angry about that, so that you can move the entire community forward.
Thanks for the report on this, John. So just comparing, you commented about like the transition to MPI. In our codes now, like the actual MPI calls are pretty
Isolated. Yes.
In the most of the code is written in a way that doesn't exhibit signs of using MPI to achieve the performance that you get from MPI. Are there programming paradigms? Does that extend to GPU programming paradigms? Are there ways to isolate the GPU-ness like there is for MPI?
This is a great question, and the unfortunate answer is it's not as isolatable. It kind of spills out all over the code, and we would love to come up with a solution for that. ISO Fortran may be a potential solution to that. I think that's the most promising things that I've seen, but it is more invasive, and that's a thing that bugs me, and that's where the analogy kind of breaks down.
Another questions. Now I'll ask one too. Building on what you said about, GPU performance is miserable until you get everything to fit in the GPU and the power efficiency stuff. So we recently ran this very large run. It was a diamond class 32 level case. It took 60 terabytes of RAM. If you do the math on that, that's 4,500 of these 40 gigabyte GPUs. But we can do that with 320 nodes. So that's a case where the problem is, like, we know if the problem's too small, it doesn't go on GPUs. If it's too big, it's also a problem, right? Like, so.
Well, you need enough GPUs.
Oh, right, okay, yeah. So, right, but without that, you can do problems that are more efficient on the CPU because you're doing the data transfers on the GPU if you don't have a big enough GPU system, right?
Yeah.
So it's finding that sweet spot. And I think that's where Mark Taylor's thing, the DOE has that sweet spot that they've either aimed at or designed for. But with a wider range of things we run, it's a little bit more challenging. You can't hit that with everything, right?
You can't hit that with everything. That's correct. But you will hit that with certain science objectives, and it's not going to be equitable. It's going to help the person who wants to do large ensembles. And it's not gonna do much for the paleo person, and it's unfortunate.
So I know this is a hard question, but just based on your group's experience, let's say we're all on board after this talk and say, okay, in the next 5 years we want to get CESM running on a GPU system. Do you have a very rough ballpark estimate for what sort of human resources we would need to allocate for that to get our 2.5 billion lines running on GPUs?
A lot. I think estimating effort is challenging. I don't feel like.
We have an example, right? I mean, look at how much E3SM has spent on this very project.
That's correct. Yes, exactly, and that's why. Okay, that's why you need to leverage other people's work. So whether that be, I hopefully I'm not going to piss people off here. Maybe you use their dynamical core that they invested 20 FTE years in or something like that, or you use a radiation package that somebody's already made that investment in, and you pull it together like this. So.
And just for the record, their investment in the die core was 35 FTE years.
Okay, so I was off. Yeah.
But as a caveat to that, there's more than just the atmosphere model in E3SM. There's a whole ocean model and a sea ice model, and there's a lot of other stuff in there. And
yeah.
So if you're talking about just taking what E3SM has done and plunking that into CESM.
Well, no, I'm not. I'm not saying. I'm not saying plunking it in, but there are reusable pieces, right? Like radiation can be reused. The Pumas microphysics. So it's yes, and some of the people have decided that a particular component model was so cheap that it wasn't worth the effort to port it. So.
I have a couple questions. The first is about data storage. I've heard of this waterfall model where big models are constantly running, and when you need data, you stick out a bucket and you get some. That's supposed to kind of obviate the need for data storage. I was just wondering, first, if you think that's the direction that we're headed in the long term. Maybe if you don't mind answering that first, I'll.
Yeah, no, I think okay. So this is the ECMWF is doing this, and I can't remember the name of it. I'm blanking at it right now. I think that's interesting. It's my thought is let them try that out and see how it works. I don't know if that's really. I don't know. I haven't thought enough about that.
Okay, thanks. And then my second question, So we had a student working here as part of the LEAP project, Anthony Zhao, who gave a really cool presentation about converting between languages using large language models.
Okay.
And I was just wondering if you have a sense of whether that's a place where industry is really going and these tools could be much more mature in 5 years. Should we wait for that technology to advance, or is it, I guess we're
I,
talking about all these huge efforts. If that's technology that's in the pipeline, what should our strategy be to leverage that?
okay, so I'll pick on Allison in this regard. So, I'm gonna now I'm gonna tell about what I'm gonna tell about what she did. So the samurai work. This was that we got 120 factor of 120 speed up. A big chunk of that, I think, a factor of 9 was from her reworking the numerics of the code because she looked at it and she decided it was not efficient, and so she went and did that, and then you got a factor of 5 or something for putting on the GPU, and then you got a factor of 3, and so you whatever that all. I'm not doing multiplication here in real time really well, but the point is, I don't believe that there's going to be a large language model that's going to be able to look at the numerics and say, oh, you're doing this wrong. So I think that there's certain stuff that it will do well, but not everything. I mean, I think and another way that I could approach this was that adding the directives was pretty easy. But what you would, where the challenge was is there was certain subroutines that were kind of just weren't written right. And so they weren't amenable to the GPU enablement. And they weren't particularly fast on the CPU either, but it wasn't like a killer, but it was a killer on the GPU. And so you had to actually think about it a lot. You had to go back and rewrite it. And then you would add the directives, which was a trivial activity, and then it ran better on everything. So that kind of, whether it's redoing the numerical algorithm or rewriting the whole subroutine because it was just not written well to begin with, this is not an automatable thing in my mind.
I have a question. Thanks, John. And so you brought up the lossy compression as a means to streamline exascale.
Yeah.
Along the same lines, and perhaps even more controversial thing that could be thought of as mixed precision or lower precision of computations. I wonder, what do you think about the feasibility of that?
I think that's, yes, I think you can do that. I think it's quite challenging to know what you can reduce the precision on. It's sometimes you get speed ups when you reduce the precision, sometimes you don't. It's not always a given. So that's kind of quite challenging, I think. I think it's a very challenging way to get at your additional speed up.
I just want to make a comment on the waterfall data and also the, not knowing about which variables to save. I think that, according to the survey, people are having way more trouble getting storage than compute time. And like saving a bunch of restart files takes way less than saving all, 600 variables. So I mean, kind of an intermediate thing is that you don't save all the variables and you save the restart piles. And if a particular scientist realizes they want something, they go to the restart and they rerun the period they want with the variable they want. And that's more efficient because it doesn't use as much storage because the restart files are very small compared to all the other data. So that's something that I don't think happens that we could take advantage of.
Any other questions? We've got time for maybe one more. Anybody want to be put on the spot? All right, then I'll give you one more question. So this is the Exascale Tiger Team report. What is your personal feeling? Like, what should we be doing, focusing more on to take advantage of this?
I think my opinion is kind of encapsulated in this. I think that everybody's challenged with data, so you should you should do your best to fix the data problem, or and I know it's multifaceted. It's not just like a link in a library, but because if you have that capability in there, then people that may be less sensitive to answer changes can take advantage of it sooner rather than later. So.
And then I'll build on one of the earlier points that you made, that it's just a matter of prioritization, because, like Alice and I have talked about this, and I actually owe her a box of chocolates for taking so long to get to it, but there's so many other things going on from SEMA and high res, and we just have to kind of prioritize and get it.
Yeah, I think it's critical for prioritization and prioritization for funding, and I think that the institution needs to fund this, and for this particular activity, not money that could be moved around to backfill some other hole.
Yeah, John.
You were right on the edge of my question I didn't want to ask, because I didn't know whether I wanted to say the answer. What's next then? So you produced this report, but this is a report saying there's a lot of things that are important and need to be sorted out and everything. Where does that go, and then how do we do the work that? Because the next stage obviously is that we've got to work out what we absolutely have to do. It's an absolute no-brainer that you got to work out what you got to do. You got to look in 10 years ahead, work out what things would look like, and work out what that means for what NCAR does and what specifically CGD and CSM are doing.
Yeah.
So how does that happen?
I think that each of the laboratories actually has to come up with a plan, and commit to it and say, I want to, you could take the recommendation whole cloth. I'm not expecting that, or you could maybe, take a couple items out of this and say, this is what our priority is, and then, you talk to the top of NCAR and say, we really need X number of FTEs to do this, and we care about this because it's going to advance these particular science objectives. I mean, I think one of the things is like lead with the science. What science will this enable, right? And that's how you justify the investments.
All right, that's a great way to end. So let's thank John again. Thank you very much. And yeah.
Yeah.